হ্যালো,
Yes, sir.
Yes, sir.
বলছি তোমাদের বৃহস্পতিবার দিন 1:30 থেকে কোনো ক্লাস আছে থাকে? হ্যালো,
স্যার সেশনাল চলে তখন।
সেশনাল চলে? বৃহস্পতিবার কি সেশনাল থাকে?
স্যার একজনদের একটা সাবসেকশনে ওয়ার্কশপ থাকে, একজনদের অ্যাপ্লাইড মেকানিক্স ল্যাব আর একজনদের ফ্লুইড মেকানিক্স ল্যাব।
আচ্ছা, ওটা শেষ হয় কি দুটোর সময়, দুটোর মধ্যে শেষ হয়ে যায়?
হ্যাঁ, মানে 2টোর সময় শেষ হওয়ার কথা, মানে শিডিউলটা।
তো এই বৃহস্পতিবার আমার একটুখানি আগে বেরোতে হবে, ওটা কি আমি 2টো থেকে নিতে পারবো? এই বৃহস্পতিবারটা
স্যার এই বৃহস্পতিবার তো বোধহয় রিপাবলিক ডে স্যার।
হ্যাঁ, বুধবার।
বুধবারই তো। বৃহস্পতিবার 27 তারিখ। খুব অসুবিধা হবে এই সপ্তাহটা 2টো থেকে নিলে?
স্যার ওয়েডনেসডে নিয়ে নিন না স্যার।
তোমাদের হ্যাঁ,
স্যার ওয়েডনেসডে নিলে ভালো হয়, সিআরদের সঙ্গে একটু কথা বলে দেখে নিন। কেন আমাদের স্যার অনেকজনই আছে এই আরসিসির জন্য যাচ্ছে স্যার 26 তারিখ থেকে।
না 26 তারিখ আমি পারবো না, 26 তারিখ অন্য একটা কাজ আছে। তোমাদের কি মঙ্গলবার রাত্রে কোনো ফাঁকা থাকে, বা কালকে তোমাদের সারাদিনে কোনো ফাঁকা আছে?
কাল সকালে ফাঁকা।
কটায়?
10টা।
না 10টা থেকে তো আবার করতে যাবে। কালকে বিকেলের দিকে কোনো ফাঁকা আছে 4টে থেকে? হ্যালো,
বিকেলে তো স্যার 2:30 থেকে সেশনাল স্টার্ট হয়ে যাচ্ছে সবার।
ও ঠিক আছে, তাহলে ওই বৃহস্পতিবার দিন 2:30 থেকেই নেব। ঠিক আছে, একটু আগে এসো, 2:15 টাইম দিলাম আমি, যাতে 2:20-25 স্টার্ট করে দেবো। আমি হয়তো 3:30
আচ্ছা স্যার, ঠিক আছে।
2:15 আমি টাইম দিয়ে জয়েন করবো। ঠিক আছে,
ঠিক আছে।
মেটেরিয়াল 2টা পেয়েছো তো?
হ্যাঁ স্যার।
আমরা কি স্টার্ট করব?
Yes, sir.
So this is the second presentation under machine design 1 or design of machine elements 1. And under the presentation 2, we will try to cover on materials, because materials is an aspect in machine design. There are different aspects for material which are related to machine design, like mechanical property. Selection of a material for a particular component depends on the mechanical property of a particular material. From the design specification or for a particular design, required material property comes from the nature of load, environment, etc. And which material can satisfy that requirement, that on the particular material. So selection of material prioritizes or rather put importance on the mechanical property, relevant mechanical property. Another aspect of the material is manufacturability. Mechanical property required for a particular component can be satisfied or can be available within a material, but ultimately the product is to be fabricated by certain manufacturing process. So as well as mechanical property, the manufacturability or manufacturing aspect of that material is also an important concern while selecting the material. It may happen that considering different aspects, the material is to be fabricated by welding procedure, and the required material property or mechanical property is available in a particular group of steel. But if it is found that that particular class of steel is not weldable at all, then it will be difficult to select that material. So mechanical property and manufacturability both are concerned to the designer while selecting the material. So first of all, we will try to understand, though this is not the class where you should learn the mechanical property, it is only associated class, because in your engineering mechanics and strength of material or material science, already you have learned this mechanical property. But as a designer, you also should have an wide awareness regarding the material property and standards available for it. We have to know the material classification, wide classification of material. And then also material are designated by some nomenclature, some standard representation, so that from the material catalog, observing the material designation, designer can introspect or can interpret what kind of material it is and what may be the probable mechanical properties of that material before selecting the material. So these are the topics to be covered under this presentation. So first I will try to discuss on material property. Most of the knowledge or most of the things now I am going to discuss probably is known to you, if not only for revision. So the first material property that you have already interacted, I think, tensile test. Have you performed the tensile test in your applied mechanics lab?
No, sir.
Not till now, sir.
Stress strain curve you have not developed, no?
No, sir.
So first, so then I have to discuss it. The first, material behavior when a material is subjected to load. Because of the constraint, strain occurs inside the material. Do you agree?
Yes, sir.
And what can be the alternative reaction to load? One kind of reaction is that it will be strained, deformation will take place, and another is it can move. If it is not constrained, if it is free to move, then motion will be the reaction by the material or by the component against applied load. I think you can categorize these two performance or two material behaviors separately. One is motion under the applied force, another is deformation under the applied force. Whenever material constrained to move freely, then deformation will take place. If material is free to move, then instead of deformation or deflection, it will move. Nature of the constraint present, deformation is a kind of response by the material when it is subjected to some load. Is it clear? Or any question? Hello?
Yes, sir, clear.
So now our area of interest is deformation. When material is constrained or component is constrained but subjected to load, a kind of response shown by the material that deformation takes place inside the material. And because of this deformation, strain occurs. Strain quantitatively means total elongation or total deformation against unit length or unit geometry. What will be the extension over unit length? That is the value of strain measured quantitatively. And the nature of the strain may vary depending on the nature of the load applied. Sometimes the strain may be longitudinal in nature, sometimes strain may be shear strain in nature, sometimes it may be volume strain in nature. Depends on the applied load, nature of the applied load. Do you agree?
Yes, sir.
And now, due to strain, another compulsory behavior of the material that it tries to restrict or avoid the strain, protest, contest, resist the strain. And how it can do it? It responds through stress. The resistance of the material against straining is reflected by developing stress inside the material. Stress is developed. You may ask why you are telling stress as resistance, response to resistance? Because due to the stress developed inside the material, the direction of the stress will be opposing to the applied load. And based on the stress developed inside the material, resisting load against applied load will be developed inside the material, because stress multiplied by the area will give you the load. So resisting responding load is in the direction of stress, which is in the opposite direction of the applied load. So the resistance load developed due to stress will counter the applied load and ultimately will create equilibrium and ultimately will stop further straining. As it happens, we can say material is rather have any material having resistance against straining. Stress is the response of these resistance, and ultimately stress gives the value of counter force, which ultimately counter the applied load and creates equilibrium, stops further straining. Is the idea clear?
Yes, sir.
So now this is an interesting area, material response or material behavior against deformation under applied load. So people try to model this material behavior and try to develop correlation between stress and strain for material. And the first formulation or first such kind of correlation was given by Robert Hooke, you know. And his finding was applicable with restriction. What was the restriction? That if the deformation is elastic in nature, so a word came in material behavior, the call which is called elastic. And what was the definition of elastic? It means that due to application of external load, deformation may take place. But if it is observed that at the withdrawal of the load, the occurred deformation or strain will be restored, will be relieved, and the component or the material will reach to the original shape and size and position without any permanent strain, then this behavior is called elastic. And Hooke's law was given only for elastic response. Then what will be the relevant question here? That is it true in every situation for all the material under every amount of load that material will behave elastically? The answer is no. It is general observation that up to a certain limit of the stress value inside the material, the behavior of the material is elastic in nature, and beyond that stress limit, the material behavior may not be elastic. How? The strain developed inside the material may not be restored fully if we exceeds that limit stress. And what is the name of that limit stress? Elastic limit. So beyond the elastic limit, the material behavior, of course, is not elastic in nature. What is the indication? If we withdraw load beyond the elastic limit, all the strain cannot be restored. A part of the strain may remain as permanent strain. Then you can ask, then what is the name of this domain when material exceeds the elastic limit? People gave the name of this domain as plastic deformation. Against elastic, the word came plastic. You may ask, how can we identify the plastic? First, very simple answer, if the strain is not fully restorable, if strain is not recovered fully, then it is the plastic strain. At any point of loading, we can subdivide the strain within the material into elastic strain and plastic strain. You may say, how? If we withdraw the load, unload, then the strain that will be recovered is called elastic strain, and the strain which is not possible to be recovered, that is plastic strain. So material behavior can have two domains, elastic domain and plastic domain, elastic region and plastic region. And the nature of the stress and strain relation, stress-strain relationship is not same in elastic and plastic. They are different. In elastic limit or in elastic region, it is observed that strain and stress relationship is more or less linear. More or less linear. A linear or proportional relationship if the limit of the stress is within elastic limit. Stress-strain relation is proportional as suggested by Hooke. But in the plastic domain, the relationship is not linear. It is a non-linear relation. And it is not fully recoverable. And if we go further into the material, if we try to correlate this elastic behavior and plastic behavior in microscopic or microstructure constituent of the material, it is general observation that the bond between the atom inside the material can be distorted in the elastic region, can be deformed, but not broken. But in case of plastic deformation, it is observed that the bond between the atom will break. And as it is broken, if it is distorted, then distortion can be restored, can be recovered. Therefore, elastic strains are recovered. But as the bonds are broken, it cannot be rejoined in a reverse way. Therefore, at the withdrawal of the load, the strain is not possible to be recovered. Therefore, it is the plastic strain. Is my point clear or any question?
Yes, sir. Clear.
Hello.
Yes,
Yes,
sir.
sir. Clear.
So now designers' interest, how this material behavior in elastic and plastic domain vary from material to material. It will vary from material to material. In case of elastic domain, we are interested in only one parameter. What is the slope of the line? We know the line is a straight line. Slope will vary from material to material. And what is the definition of this slope? I think you know modulus of elasticity, isn't? The ratio between stress and strain is given by modulus of elasticity.
Yes.
And different material will have different values of modulus of elasticity. And in this domain also, another parameter called Poisson ratio, that is also another material parameter. So within elastic limit, designers have only two material properties to be considered. One is elastic limit, another is Poisson ratio. Are you sure or not? Hello?
Yes, sir.
In beyond the elastic limit, it is observed that if we increase the stress, increase the load, or rather increase the strain, what will happen? Stress will continually increase up to certain limit, and then it will fail. The curve is given in the bottom that stress developed inside the material will continuously increase with strain and will fail at a point, which is called, or rather, failure stress or fracture stress. Is it understood?
Yes.
Hello? Yeah. This will be the nature of the curve when we measure true stress and true strain. You may ask why the word true comes? Because during the experiment, we applied load at the end. And to calculate stress, we divide this load by the cross-section area of the member. Now a question will come. During the loading, a time will come when area will be reduced inside the material, which is called necking. This thing will occur. And this reduction in area will grow, will be increased if we increase the load further. And a time will come, a narrow cross section will be there in this region, and then material will fail. So during the loading, the area of the material at certain cross section will reduce gradually. And if we have to calculate the stress at that cross section, we should divide the applied load by the modified or reduced cross section area, isn't, to get the real value of stress.
Yes, sir.
Do you agree with me or not?
Yes, sir.
Yes, sir.
Yes, sir.
So, bolo. So whenever stress is calculated considering the reduction in area, stress is called true stress. Similarly, strain is defined by the total extension which we measure divided by the gauge length of the material. Is shown here this, and we can measure the extension over this length. dividing the extension by this gauge length, we can measure strain. But again, during the deformation, as area is reduced, the gauge length also will be increased in length, isn't it?
Yes, sir.
So for calculating actual real proper strain, we have to divide the deflection obtained by modified gauge length. Modified length is called true strain. And if we measure true stress and true strain, then stress versus strain curve will be like this. It will continuously increase. Stress will continuously increase with strain if it is a true stress versus true strain curve and fails at certain value. That point is fracture stress or failure stress. And another point is here, the bending of the line from linear relationship, which is called yielding. Yielding. When plastic deformation starts or exceeding the elastic limit, the point on the stress strain curve is called yield point or yielding. In the stress strain curve, there will be a sharp point below which the region is elastic and beyond which the region is plastic. This point which separates the stress strain behavior into two domains is called yield point. Yield point. Yielding means onset or starting of plastic deformation. So if we consider the true stress strain curve, we can identify a point which is called yield point and another point which is called fracture stress or failure stress. Yield stress and failure stress on the true stress versus true strain curve. Do you agree?
Yes.
Yes, sir.
Yes, sir.
But our general practice in experimentation not to consider the change in the length or change in the cross-section area. We have given input the initial cross-section area and initial gauge length as input, and we divide the applied load by the final area to get the value of stress, which is named as engineering stress. Similarly, we divide the extension obtained by the original gauge length without any modification, and thus obtained strain are called engineering strain. Now, if we plot engineering stress versus engineering strain, then the nature of the curve will be like this bottom curve. What is the nature? Specific feature? The value of stress starts to be nonlinear at certain point, which can be identified as a yield point. Then it increases up to a maximum value and then starts to fall and then fails at certain point. Can you distinguish between these two curves, the engineering stress strain and true stress versus true strain?
Yes,
Hello. Now you should have a question why in the engineering stress strain curve we get a maxima. Why the failure stress is below this maximum stress? These two questions is an automatic query from your side. Is it true?
Yes, sir.
Yes, sir.
Hello?
Yes, sir.
Hello?
Sir, can you hear me?
তোমরা কি আছো না নেই? তোমরা আমার পয়েন্ট
হ্যাঁ
Yes,
আছি
sir.
স্যার, শুনছি স্যার সব।
Sir,
Sir, the response.
So in engineering stress, the maximum stress obtained on the curve is called ultimate stress. It is a very important material property. From experiment, we measure this value of maximum stress on the stress strain curve. And this point is known as ultimate stress. Ultimate stress. And sometimes for evaluating material strength or assessing the material strength, we assume that this ultimate stress value is the maximum stress which can be allowed inside the material. So this is the limiting point for material strength. This is the limiting point for material strength, ultimate stress. So from the stress strain curve, if it is engineering stress strain curve, then we will get a maxima which is known as ultimate stress. And there will be a stress at which material will fail, which is called failure stress or fracture stress. So there are three different distinguished points. Yield point, where plastic deformation starts. Ultimate point, the maximum value of stress during the experiment, and breaking stress or failure stress or fracture stress, the value of stress at which the material fails. The question is why such things occur? Because this is the limitation of measuring procedure, because we measure the stress not from the internal response. We are not measuring the internal response directly. Rather, we are calculating the internal response stress as applied force versus cross-section area divided by cross-section area. Now, what will happen that when necking starts, the cross-section area is reduced. Though the value of stress is very high, load-bearing capacity of the system will be lowered. Do you agree or not? As area has been reduced.
Yes.
So now we measure the load as reaction. We have applied extension on the material. Because of that, strain occurs. Because of that, stress is developed. But load is given by the reaction. Value of reaction is calculated by multiplying the stress by the cross-section area available. And during the necking, as this cross-section area is reduced, so at this point of stress, though the stress is very high, load will be not so high. Do you agree with me or not?
Yes, sir.
So what happens as we calculate stress from the applied load value? So this is the point, this ultimate point, ultimate value of stress is the point where necking starts. And while necking starts, as the area is reduced, load will fall. And as load is dropped, when we calculate the value of stress from the dropped load, the value of stress is appearing to be lower, though it is not lower. Beyond the ultimate point, the stress showing lower, but it is not actually lower. As we are calculating the stress from the load, and due to the reduction in area as the load coming to be lower, so calculated stress, engineering stress is coming to be lower. But if we make the necessary correction, then we will get true stress versus true strain, where there is no maximum, where failure stress is the maximum value of the allowable stress. Is it clear to you or not? The difference between engineering stress strain and true stress strain. In engineering stress strain, we get three material property: yield point, ultimate, and breaking stress. In true stress strain curve, there is no existence of this ultimate or maxima. It is continuously increasing, and fracture stress or failure stress is the actual value of the maximum stress. Is it clear to you or not?
Yes, sir.
So to model or to characterize the material behavior in the elastic limit, we require only one property, elastic modulus and yield point, because yield point will show how far, how long it is elastic, and elastic modulus will show what is the slope of the curve stress strain within this limit? Is it clear?
Yes, sir.
Another property is obtained from plastic domain, which is called ultimate stress, which is also named as tensile strength. Another property which is called breaking stress or failure stress, and also one information, the value of strain at which material finally fails, which is called failure strain. So failure point can be given either in terms of stress, breaking stress, or in terms of failure strain, fracture strain, rupture strain. Do you agree?
Yes, sir.
And measuring technique is that a longitudinal specimen, round specimen, is gripped between these two grip, and here load cell is there. It is extended by some servohydraulic actuator. Extension is measured between these 2 points, which is called gauge length. So extension is measured and load is measured. Now in post-processing, dividing the load by area, we will get stress, and dividing the extension by gauge length, we will get strain. So that will be plotted. So we will get load versus extension curve, and from load versus extension curve, we can convert it to stress versus strain. And during conversion to stress versus strain, it may be true stress versus true strain, or engineering stress versus engineering strain. In case of true stress to strain, we will get elastic limit, yield point, and fracture stress. In case of engineering stress strain curve, we can get elastic limit, yield point, tensile strength or ultimate stress, breaking stress, failure strain, and another property also is called toughness, which is nothing but the area under the stress strain curve. Area under the stress strain curve, which measures the toughness of the material. And in the plastic domain, it is observed that the value of stress is more than yield point by certain amount, and this is called hardening. The value of stress is more than yield point, and this extra stress compared to yield point is called hardening of the material. Because in case of fully or perfectly plastic material, after yielding, there should be no increase of the stress value, as because plastic deformation have taken place. But depending on the material, it is observed, no, it will not happen in that way. Rather, the stress can be increased by certain extent in the plastic deformation. And this extra amount of stress which can be occurred within the material during its plastic deformation is called hardening. Hardening. What is the hardening at this particular point? We can measure the stress by subtracting the stress value here, by subtracting yield point. This amount is hardening. Hardening. Have you understood by hardening?
Yes, sir.
Yes, sir.
And this amount of hardening will vary from material to material. Strain hardening will be different for different material. And this behavior, what is the name of the behavior? Strain hardening. What is the region where it is observed? Beyond the yield point. How the amount of hardening is measured? The value of stress at that point subtracted by yield value of the, or yield point stress of the material. This is called hardening. And this amount of hardening varies from material to material. For a particular material, this amount of hardening also vary with the strain level. With the strain level, look, the hardening amount have been changed when strain increases. So there is a relationship between hardening of the material versus strain. Hardening of the material versus strain. And this relationship also vary from material to material. Now, if we try to model this relationship, what is the parameter? One is hardening, another is strain level. Hello, class achi. Class achi. So that can be modeled by some nonlinear relationship relating the sigma at the plastic domain versus strain. Strain. One of such kind relationship is given by this power law that stress is equal to K into epsilon T to the power N, where epsilon T represents the total strain and K represents the one of the material property, which is called strain hardening coefficient. And this N is also another material property, which is called strain hardening exponent. Another kind of relationships are there, that sigma versus strain can be expressed by some exponential law. Exponential law. So there are several material law to represent, to characterize strain hardening zone of the material, to correlate stress and strain in the plastic domain. They are called strain hardening material law. One of such kind of law is given here. And the material property K and N can be calibrated if these data are available. Data, several points, on several points we can measure the value of stress and strain. And now if we plot, we will get simultaneous equation, two set of simultaneous equation. By fitting log versus log plotting, we can measure the K and the epsilon N. N will be measured from the slope and K will be measured from the intercept. Thus, K and N can be calibrated, can be extracted for a material if we know the value of stress and strain in the plastic domain. So these are the important material properties which can be measured from the plastic domain. Is it understood?
Yes, sir.
Yes, sir.
So this is the total material property which we can extract from a tensile test from the stress-strain relationship or response curve. You agree with me or not? And all these things are standardized. The test procedure, how you will extract data, how you will continue the test, are already standardized by ASTM, American Society for Testing Materials, and their code name is given by E8. E8 depicts or describes the standards to be followed for tensile testing. Up to okay?
Yes, sir.
আর কোনো কনফিউশন আছে? Now, from the stress strain curve, we also can measure the ductility of the material. What is meant by ductility? Some materials allow huge plastic deformation before failure, and some material will not allow at all any plastic deformation before failure. So the extent of plastic deformation occurs before failure will vary from material to material. And this degree of extension or degree of plastic deformation is generally reflected by a property called ductility. Higher the plastic deformation before failure, higher the ductility of the material. And the reverse of the ductility is called brittleness. If any material doesn't allow any sufficient plastic deformation before failure, the material is termed to be brittle material. This behavior of material is known as brittleness. Brittleness. Now you can ask, from the stress strain curve, can we identify which one is brittle, which one is ductile? Yes. You just look, what is the value of fracture strain before failure? If it is low, the material is brittle. If it is high, the material is ductile. And by measuring the fracture strain, you can represent the ductility of the material. The strength of the material, look here, strength of the material is high compared to this material, but ductility of this material is high compared to this material. Ductility high means toughness high, as because area under the curve will be more in the second case compared to first case. The energy absorbed by the material before failure is high in case of ductile material and low in case of brittle material. Is it clear?
Yes, sir.
But whenever the rate of loading is very high, if the load is applied as impact load suddenly, then the nature of failure cannot be described or explained by the stress-strain relationship of the material. It will not happen that the material will fail as because the developed stress within the material has crossed the permissible value of the material stress. It is observed here material is failed as because the amount of energy absorbed inside the material exceeds permissible energy to be absorbed by the material. That means toughness will determine the failure. Toughness is the property which will determine the failure. And there are mechanical structure where the nature of the load may be impact in nature. So failure of those members should be described, should be designed on the basis of their strength against impact loading, on the basis of their toughness. So toughness is a material property which is to be measured by some standard procedure. Those standard procedures are IJOT testing, Sharpie testing, Baker's testing. General different class of impact testing are there. And what is the standard procedure? The specimen is made up with some notch and gripped here, and a pendulum is raised to certain height and released. It will strike the specimen and will create fracture. After creating the fracture, the pendulum will go up to a certain extent, not to the full height from where it was released. And difference in height for these two positions will give you the, from this height, we can calculate the potential energy lost by this pendulum, mgh. And that amount of energy is absorbed by the material before failure. So if we can measure the height raised after creating fracture, then we can calculate the energy absorbed or rather energy lost by the pendulum, and that lost amount of energy is assumed to be absorbed by the material before failure, and that represents the toughness. By impact testing, we measure toughness of the material, and those values are represented by IJOT number, Sharpie number, etc. There are standard procedures. By comparing the Sharpie number, by comparing the IJOT number, a designer can anticipate what is the relative toughness of the material. And if designer is aware or concerned that the nature of the load is impact in nature, then he will try to assess the quality of the material or acceptability of the material on the basis of their relevant Sharpie number or IJOT number. Is it agreed?
Yes, sir.
Fracture toughness or fracture resistance. So far, in your strength of material, in your undergraduate courses mostly, you will study the material assuming it to be continuum. Means there is no crack, there is no void, there is no discontinuity within the material. Material is a continuum. Still it can fail. Then you try to explain the failure in terms of stress, strain, etc. But in real life, material always will have discontinuity, small, tiny cracks, voids, etc. And when there are discontinuity in the material, then the stress-strain relationship is not like when material is assumed to be continuous. And as real-life materials are containing cracks, therefore sometimes design based on the strength of material will be not matching with the real life happening. Your prediction may not match with the real life happening. There, for better matching, for accurate analysis of the material behavior against load, you have to assume a crack inside the material, a defect inside the material. And the value of stress at which material will fail, it is not only a material property, but depends also on the size of the crack present. Higher the crack, lower the value of failure stress in the material. That means the strength of the material is not only material dependent, but also it has dependence on the size of cracks present inside the material. And whether an existing crack will grow under the given load or not, that is to be measured by some other property. The material resistance against crack growth is measured by the fracture toughness. Fracture toughness. Is it understood what is meant by fracture toughness? It is the resistance of the material against crack growth. Against crack growth. Hardness is another kind of material. It is the resistance of the material against abrasion, scratching, indentation. I think you know the word abrasion. Hello? Loss of material due to rubbing. Scratching
Yes,
is the mark on the surface because of some sharp forces, and indentation is some deepening on the surface, local plastic deformation. So material resist abrasion, resist scratch, resist indentation phenomena on the material. But this resistance of the material will vary from material to material. You should have query that which are the basic property on which this property depends. Yes, material, ultimate stress, yield stress, these have bearing on this resistance. But they are not only the sole property. It is an integral property by which you can represent or you can measure the hardness. And how hardness is measured, it is a very simple experiment. We applied a load on the surface. We measure the load and we released the load. Then there will be a permanent deformation on the material, permanent groove. We can measure the diameter of that groove. We can divide this applied load by this diameter. We can divide the applied load by this diameter. Then that will give you that to create unit groove of unit diameter, this amount of load will be required. That will represent the hardness value. That is the Rockwell hardness value. But Brinell will measure dividing the load by the surface area created by this group. Knowing the diameter and knowing the depth of indentation, we can measure the surface area and divide this surface area, divide the load by this surface area, we can evaluate the Brinell hardness number. Different hardness testing procedures are there, Rockwell, Brinell, Vickers, etc. Measuring methods are different, but always it will give you the resistance of the material against indentation, scratching or abrasion. These are known as hardness. And sometimes also design interested to correlate this hardness value with the tensile strength of the material. And from experiment, people tried to give some idea to correlate the hardness versus strength of certain class of materials. The advantage is measuring hardness is not very difficult. If we have such kind of relationship available, then just by measuring hardness, we can anticipate what can be the probable or possible range of tensile strength of the material. Have you understood?
Yes, sir.
Yes, sir.
So I am ending here because we have no time further. For fatigue and thing, in the next class I will discuss. Okay.
Okay, sir.
Okay, sir.
On Wednesday, instead of Thursday, on Wednesday, if I can manage certain time between 2 to 4, are you ready for taking classes? 3 to 4, or it will be complex for yourself?
স্যার রিপাবলিক ডেতে তো এমনিতে সব ক্লাস থাকে না, তো ছুটিই থাকে তো।
না, সবাইয়ের এগ্রিমেন্টটা দরকার, যেহেতু ওটা মানে কি বলবো, তোমাদের ছুটি আমার ক্লাস, ঠিক আছে, বাদ দাও, ওটা করলে আবার ঠিক। আমি বৃহস্পতিবার দিনই ওই 2:30 থেকে 3:30 অব্দি ক্লাস নেব, ঠিক আছে?
ঠিক আছে স্যার।
তোমরা বুঝতে পারছো তো?
হ্যাঁ স্যার।
Sir.
ওকে। চা করে দিলাম।